So, continuing our journey, we need to actually bring more liquid into this. And the way we're going to do it in this lesson is not the way we did it last lesson. Last lesson we used a volume source. Volume source is cool for like having water pour into something, things of that nature. For simulations that are part of a larger simulation, like ocean stuff also does this. But again, for us, a river that has water coming in and water going out, it's really great to use this thing on the flip solver here called use boundary layer. Use boundary layer basically allows us to specify a padding away from the boundary. So the boundary is, of course, the box, the literal boundary of our sim, the maximum one, I should say. And we can say, like, if this is X, Y, and Z, and lower padding meaning the lower, the negative X, negative Y, negative Z sides, and the upper padding is the positive ones, then let's say the lower X means that if I were to say, I don't know, 0.5 units into the simulation from this side, every single substep, it will look at whatever we have listed here. I'm going to turn this on too, apply boundary velocities, because we want to do this for sourcing water and also for sourcing the velocity of it. It will look in 0.5 from here, and it will replace whatever it finds with particles that it'll find an SDF surface. It will fill it with particles based on, our particle separation here. And then it will also sample the velocity volume in that same space to give those brand new particles a reason to live. Now, as opposed to the volume source method that we started to talk about here, which certainly sources flip and things of that nature, but what it does, at least by default, is it will kind of union the incoming fluid with the fluid that's already there. Now, there are ways around that, but this is just a nice, clean way of doing it anyway, because that is what this is meant for. It replaces it, and then you always have this particles pushing in from the side, and then you'll also have particles exiting from this side, and the pressure calculation in general will kind of have like a suction on this end and a pressure push in on this end. So we'll have a nice flowing river. I'm going to say, actually, 0.5 on both of these. I want 0.5 on the X here, and the 0.5, like I said, as these kind of suction on that. And I'll give you an idea. So if I just press play now, nothing is happening because there is nothing here. But for the sake of argument, I could put the initial state here, and you'll see, over here I mean, you'll see that happening. Here it is, the first 0.5 units, it's sampling this one. Remember, there is actually a surface here, which is what this is looking for, a surface volume, which we do have. So it's just looking at the first 0.5 here, and again, plain as day, it is bringing them in. Now, what it's not doing really is they're not really moving. It looks like they're moving. They're not actually moving. They're just being scattered in different locations on every frame. That's why you don't see water literally moving into this, though. They're just coming in, but they have no velocity. There's no velocity volume. If I were to put this here too, well, that doesn't change the fact that there's no velocity volume. So we need to come up with maybe even a better initial state surface and also a velocity volume. So I would like to start from this. I just want to chop off all this in middle stuff, because although it does a good enough job at only sampling this area, when I have higher resolution sims later on, and these will change every frame as I change the velocity field and the actual shape of the incoming liquid every frame, I don't want to have to recalculate all of this every frame when I can just recalculate these little trimmings at the edge. So I'm going to drop a box down that's going to represent the rest of the fluid sim. And what I mean by that is I'm going to grab the box size, Paste that. I want the box center. Paste that. So you can see so far, it's, it's the same. It is the same as the bounds. And now I need to accommodate that fact that we need to push in a little bit on the sides. I'm going to use a bound because that's essentially what this is doing. You can see lower padding. It's the same nomenclature. So I'm going to say paste relative references here. You'll see it's making it bigger. Paste relative references here. So I, of course, just need to do the opposite. Now I'm going to do them for all of them, even though we know we're only really going to do it with the X. But for the sake of completeness, we now have a robust solution that you can use if you wanted to remake this. Cool. So we have essentially our entire simulation minus the bounding area, as is compared to this, which was our initial thing here. So really all we need to do is VDB combine here to make that, and then, or rather, VDB from polygons to make that, then VDB combine to do that subtraction. Let's actually start from this one, because this one already has the subtraction from the collider. So go from that to that, STS difference, and there you go. Now we have a much smaller area that we can play with here. So the first thing we'll do is let's work on the surface. The new surface, I mean, the incoming source surface. So let's convert this to polygons. The resolution is tied to, it's very low resolution because that's what we're dealing with right now. As we change this, everything's going to change. So I'll even keep it like that for now. It's just so we have more to work with. So what I want to do here is I'll drop a mountain down to kind of mess with it. Now this we want to be tied to the time. So I could say like literally time, and now it's animated over time. It doesn't move very fast, so we'll probably want to multiply it by some number, like so. And now it's just looks like it's a slice of water. We're just getting like a, just a slice of it in space. Now we don't want to move this high up, so I'm saying like 0.1. And maybe if we have the element size be smaller. So that's pretty good. We don't want anything to be too crazy. Most of our simulation will happen anyway, regardless of the incoming craziness here. But just enough to have it start off to be something a little bit more interesting. Let's do the whirly again, because I like it. So that's cool. Maybe we won't do center noise in this case. Yeah, just keep it a little bit bigger. It's probably fine. So there you go. We can now do a flip source here. In fact, we can just copy the same one from before. Like so, because it has all the same stuff set up for it already. This somehow got moved. There we go. Now this being a VDB, it's not storing all the data in between these two. So this is a lot more efficient, especially again at these higher resolutions that we'll be getting into. So that's pretty cool. I'm going to put a null here and say that this is the surf. I'll say this is maybe the boundary surf. So that's cool. And what else we need? We're going to want to make velocities also. Now, as again we get to higher resolutions later on, we don't need necessarily for our incoming velocity field to be so insanely detailed, because this was going to get pretty small later on. I just want generally a velocity that is sending it this way and is maybe perturbed a little bit. So we don't have to go too crazy on that front. I'm going to say, let's do a points from volume. We can start it from, well, actually we can start from this. Oopsies, there we go. And it makes a nice little grid of points. And now, of course, we would normally think to do particle separation here, but like I said, I want to just do it manually. I say this here, what I have here, is a high enough resolution. Because like at this distance, you know, like that's enough. I don't want to, we're going to have to recalculate this on every frame, as you can see. And I want to keep it fast. I don't want this to impact my simulation time. So I'm going to hide everything else here for a minute. Okay. And we want to turn on add scale attribute, which will make a P scale here. This will be important because we're going to want to stamp whatever the data we put on this. We're going to put a velocity per point on here. Let's just do it. I'm going to make an attribute wrangle, and I'll say, hey, the velocity is equal to some channel vector channel, and we'll say, call it something clever like velocity. So whatever this is, the V is going to be. What should this be? Well, it should probably be the same as to what we already had the initial ones being. So I'm going to paste that here. So now everybody, you can see if I click the velocity visualizer, they now have that. And if I were to attribute rasterize or volume rasterize attributes, what I was starting to say before is that the scale attribute here will mean that though each particle will contribute into the final volume that we're making here the size of the particle. So the size is just how far it is essentially from its neighbors. So here we are. We say rasterize that V attribute. The voxel size might as well just be the same as what it already is here. So copy that one. So remember, we're not doing this in terms of the simulation one. We're doing this one at a fixed way. We can do a volume trail and a volume slice to visualize what we just made. So here's a slice and here's a trail. There we go. So we have a vector field. They're all just pointing to the right. And we can be assured that whatever we're doing here is happening over here also. But I'm just going to look at this side. So right now, they're all pointing the same direction. What you can do is we can do a noise, attribute noise, and say, put that after our wrangler here, and just say, let's just add to the velocity something. So I'm going to definitely want to center this. I wouldn't worry too much about this, but just make the element size kind of smaller. Maybe this is fine. Just something to kind of, you know, break it up a little bit. Maybe even one. And it mostly looks like, you know, that is moving to the right. If you were to just break this connection here and there was no velocity, now we just have like a purely interesting, oh, we should make this be animated as well. So this is how you would just make an interesting velocity field in the first place. But we mostly want ours to be governed by this again. So I'm going to remake that here, copy that onto here. It should mostly be moving to the right and just be broken up a little bit. Now this is just the visualizer. This is the actual volume. It looks like a fog here, which doesn't really do us much good, which is why we did that. But we can be rest assured that it is actually nice. So we've done it. We have now incoming liquid area and incoming liquid velocities. And these can be the things that we point to in our thing over here. So coming back to our flip solver, we can say the boundary velocity for velocity volume, and we can put boundary surface for here. And now, and I'll just keep it at our new resolution that we set it to. If you didn't do it, it's at 0.05 now. So let's see what we got. And sure enough, we have new particles coming in, old particles going out. It's a circle of life. The longer we let it sit, this is kind of what I was talking about earlier with our having a presim. it starts in this unnatural, calm state, like this. But obviously, it's a moving river, so it's not going to look like that. The longer it goes, it eventually kind of settles into the interesting shapes and waves that it wants to be, based on the actual geometry of our river basin. So much of the result of our river sim is going to be based off of where we put the colliders, what the riverbed looks like. I mean, it's really everything. How shallow the river is. You can't just have the river look like however you want. The river is reacting to colliders. That's everything. So when you're done, your river will naturally have to look a little different than mine because you'll have your colliders probably be in a slightly different spot. But in any case, so that's pretty cool. Let's actually go put more colliders in to make it more interesting.